next speaker is Robert McGough from Michigan State, and his title is Analytical and Numerical Models of Power Law Attenuation for Simulations of Medical Ultrasound.
Thank you. So, before I get into the material on the models of power law attenuation, I'd like to give a quick introduction to our FOCUS software package. FOCUS stands for Fast Object-Oriented C++ Ultrasound Simulator. And here you can see a screenshot from our FOCUS website where you can download FOCUS, you can find documentation on FOCUS, as well as other additional material. This is the web address where you can obtain FOCUS, which is a free MATLAB-based package for simulating medical ultrasound. We've spent a lot of time optimizing FOCUS for both rapid and accurate numerical calculations, particularly for near-field pressures. We apply this to both single transducers as well as arrays of transducers. Both transient and continuous wave calculations are supported by FOCUS. And in particular, we support three fundamental transducer shapes: circular transducers, spherically focused transducers, and rectangular transducers. Others, we actually also support ring transducers, which is a variation, actually two different variations of the circular transducer and the spherically focused transducer. So just very quickly to highlight a couple of the ways that we've used FOCUS. You see on the left here an example of a circular piston. On the right, we've calculated the near-field pressure for that circular piston, which has a radius of 10 millimeters, and we're providing a steady a sinusoidal excitation at 2.5 megahertz. So we calculate that pressure all the way up to the piston face. We don't have any of the issues with singularities on the piston surface that other approaches have. We can calculate this fairly quickly in about 0.2 of a second, just on a standard desktop computer using FOCUS. Then likewise, here is an example of a spherically focused transducer. In this particular example, using the same radius. The aperture radius is 10 millimeters. And then we have a radius of curvature about 14 millimeters. We use the same continuous wave excitation, 2.5 megahertz. You can see on the right a nicely focused field that we calculate once again on a large grid. This takes about 0.3 of a second using FOCUS on the same computer. Then we can also model transient calculations, and for that exact same transducer geometry that I showed you in the last slide, 10 millimeter radius for the aperture and a 14 millimeter radius of curvature. This time we excite that piston with a 3-cycle pulse, so this is a transient calculation, and then also with the center frequency of 2.5 megahertz. This likewise on the same computer takes us about 0.2 of a second on a reasonably sized large grid, but in particular we calculate that pressure at 755 time points. We'll only show you 7 slices of those here. And by the way, we're sampling the field at 40 megahertz. So we can see at first the field emanates from the spherically focused transducer, then it converges to a focus, and then it diverges away from the focus. Okay. So we're really just scratching the surface here in terms of what FOCUS can do, but I'd like to give you an idea of some of its capability. Now I'd like to get into models of power law attenuation. The simulations that I showed you previously, we can handle in FOCUS attenuation for continuous wave calculations, but at present not so for transient. And so this modeling of power law attenuation is part of our effort to address exactly that issue. So we're familiar with power law attenuation. It is described by a proportionality factor, alpha naught, multiplied by the frequency in radians per second to the y power, where in biological tissues, y is typically between 1 and 1.5. And likewise, we know that power law attenuation is also accompanied by a frequency-dependent speed of sound, which is described by this expression here. So 1 over the frequency-dependent speed of sound is modeled by 1 over a constant value plus alpha naught times tangent of pi y over 2 multiplied by this difference between these two frequency terms. This expression is appropriate for values of y between 0 and 2, but not for y is equal to 1. There's a singularity here, and so we use a different model to address that singularity problem, which is described right here. And it turns out that if we work with those two expressions in the first two equations for the attenuation and the speed of sound, and we do some manipulations, we find that those are exactly satisfied by this equation, the power law wave equation, which we derive. Power law wave equation is a fractional partial differential equation with fractional derivatives with respect to the time variable. We recognize in the power law wave equation the first two terms are the lossless wave equation. The first three terms are Szabo's wave equation. And so we're extending Szabo's wave equation really by adding this fourth term that allows us to exactly model the power law attenuation and frequency-dependent speed of sound that I showed earlier. So this is a great starting point, but there's quite a few other interesting things that we can do with this. One is that we have subsequently found the exact Green's function for this power law wave equation. And we found it both in the frequency domain, which I'm showing first in equation 5, and in the time domain in equation 6. Let's look at the frequency domain version more closely. The one thing that we should recognize from this e to the minus j omega over CR divided by 2 pi r, that's the frequency domain Green's function for the lossless wave equation. In other words, the Helmholtz wave equation. So, and then in addition, this other term in the numerator, this exponential term, this is the probability density, this is the characteristic function for a stable probability density function. So it's kind of neat. We're multiplying in the frequency domain a well-known Green's function by the characteristic function of a stable PDF. And when we evaluate the inverse Fourier transform of this expression, we get a Green's function in the time domain, which is, we see the scale factor 1 over 2 pi r that comes from the Green's function, and then the remaining terms are scaled and translated versions of this stable PDF. Now, this stable PDF has been well characterized by statisticians over the last several decades. One thing that we know about this is that the stable PDF is supported on the entire real line for values of y between 1 and 2. What this means is that these solutions are non-causal. But I'll get into that a little bit further. Actually, the non-causal nature of the solution is actually not such a big deal. What is more of a big deal for numerical calculation is the fact that these stable PDFs have heavy tails. So these heavy tails mean that these stable PDFs decay very slowly. The dominant term is this t to the minus 1, t to the minus y minus 1 power. And what this means is that relative to an exponential function, this PDF decays relatively slowly. We'll see evidence of that in just a minute. We also know that if we evaluate these stable PDFs with inverse FFTs, that we're going to run into frequency domain aliasing problems. So that's an issue for our numerical calculations. But fortunately, that's addressed if we calculate what I will call in effect the solution in the time domain with the stable toolbox, which is a MATLAB program that we've been using for this problem. So to give you an idea what a stable PDF looks like, I plugged in the value for the power law exponent obtained from the Physical Properties of Tissue book by Francis Duck. Took the value of 1.139 for human liver, evaluated this PDF. And so what we see, recall the properties that I mentioned earlier, there's the support along the entire real line. So in other words, just like a Gaussian function that extends from negative infinity to infinity, the values are non-zero, though beyond a certain point, numerically, they're effectively zero. Right? But also, we have a substantial portion of our solution that is non-zero and noticeably non-zero to the left of our origin here, where x is a unitless parameter of our PDF. Okay, so that will come into play in just a minute. Also, finally, the heavy tail that I mentioned. Here's the heavy tail. This PDF extends out quite a ways when we traverse this to the right. To the left, actually these stable PDFs do decay exponentially with increasingly negative values of x. So actually, now let's keep going. So when we use these expressions for the Green's functions in calculations of the impulse response, in effect, we're just evaluating the Rayleigh-Sommerfeld integral either in the frequency domain or in the time domain. What we find is that starting in the frequency domain, we see this result for the impulse response relative to the lossless impulse response. We see that the lossy impulse response is actually advanced. It arrives earlier than the lossless impulse response and then continues on. One of the problems, though, is that due to this heavy tail, the frequency domain aliasing, we erroneously get a non-zero result for the lossy impulse response at these early times here. So an easy way to address that is to simply calculate the result in the time domain using the stable toolbox. And what that does for us, so unlike the frequency domain calculations, we can specify a range of times over which we're interested in impulse response, and the solution will not be polluted by this frequency domain wraparound. So that's a nice feature of calculating these in the time domain. Then also, since we have these nice analytical expressions based on these PDFs, we can calculate analytical approximations for the impulse response in lossy media. For example, this is for a circular piston evaluated on axis. So to get an idea how this looks, we can calculate the Rayleigh-Sommerfeld integral. That's the darker blue line that's just barely noticeable. It's peeking out behind the lighter blue or whatever color that is line. So our analytical approximation is not quite dead on, but it's really very close. So that's just one of the neat features that we're able to pull out. There's a few other things that I'd like to mention, and I'll wrap all those up here. So what we found is that we've derived the power law wave equation, which exactly satisfies our specified models for power law attenuation and frequency-dependent speed of sound. From that power law wave equation, we've extracted Green's functions in both the time and the frequency domain. And I pushed one aspect, namely this heavy tail behavior that's responsible for the frequency domain aliasing. The fact of the matter is, we've encountered trade-offs that I don't have time to go into here, but there are advantages and disadvantages to each of those solutions. Then one thing that I didn't show, but I'll tell you a little bit more about right now, this causality issue with these Green's functions really only manifests itself a very short distance away from the source. Okay, so in other words, we worry about causality in that we apply an input at this location and then some distance away before that input is applied, that we're concerned that there might be some non-causal response. That is just simply not the case. Okay? I'd say this is analogous to far field type issues, that the far field approximation is good when you're far enough away from the source. Then likewise, these non-causal solutions are basically, they behave as causal solutions as soon as you move far enough away from the source. And far enough away, actually in a previous presentation, I showed that far enough away is on the order of angstroms, something like that. Okay, so only very close to the source is causality really an issue. Okay, in any case, back to the trade-offs between time and frequency domain calculations. We can avoid aliasing problems by calculating these responses in the time domain. And then finally, we showed that there's an analytical approximation that we can use to calculate the on-axis impulse response in lossy media for a circular test. So I'd also like to acknowledge support from NIH and then past students, both a PhD student and an undergraduate student who's now at Emory and Georgia Tech, and then collaborators, John Nolan, who wrote the very nice stable toolbox. He's at American University, and then also Mark Mearshart from Michigan State University. And then finally, I'd like to encourage you to download and try Focus, which you can find here. So thank you very much. That concludes my talk.
So we have time for a few questions. Maybe I'll start. So can you give us a sense of the practical sort of improvement that you get using these methods over more standard techniques?
So the fractional calculus modeling?
In terms of the quality, if we were to implement these and compare images generated with and without, what are we looking at? What are the main sources, main features of the improvements?
Well, I guess I'm going to twist your question around just a little bit. So really my motivation in doing this is the fact that we can calculate pressures very quickly with our Focus software in the lossless case. So what we'd like to do is we'd like to see how does power law attenuation and dispersion impact both, you saw the wave propagates, but then also what happens in B-mode images. Okay? So that's our motivation for what we're doing.
Oh. If you go back to, I think, to slide number 5, where you compared your equation with the one from Szabo, where you introduce losses, maybe a little bit later. Yes,
right here.
So you get this additional term. But when I look at the field equations, I have two field equations. I have two medium parameters, rho and kappa, volume density of mass and compressibility. So if you would compare your method and you would go back to those field equations, where do I then introduce the losses? Or is this a difficult, nasty question?
That is a very difficult and nasty question. I didn't really get into this. Our take on your question, which is it's related, but it's a little bit different, is that, and in particular, this is something I'm working on with Mark Mearshart at Michigan State. What are the constitutive equations that lead us to these fractional wave equations? And there's no short answer, but I'll get you started. Okay, these fractional derivatives indicate that we have some sort of non-local behavior. Okay? That's one of the big differences between the constitutive equations that we use to derive the purely lossless wave equation. Everything is local. Nothing jumps a cell. When you have a fractional time or fractional space derivative, there's a continuum of interactions that occur instantaneously as opposed to flow from one cell to another. So what these do, and I'm changing your question too, but what these do, they show this kind of memory in the system that is really, it's not present here.
So you're basically then introducing some kind of relaxation function.
A relaxation model is another or a similar way to look at this. We haven't really looked at relaxation, but I'm aware that you can use relaxation as a way to model these effects. I wouldn't say that we're using relaxation just yet. And I'd also add, I'll throw out another kind of a plug, we're also working on stochastic models. And what are the underlying stochastic processes that ultimately lead us to these time fractional derivatives? And so that's something that's coming. It's not there yet, but it's coming.
All right, thanks again.